that appears in those white gaps on this diagram is something you're going to miss, and so you've got a trade-off of how quickly you sweep for what you might see or miss. And then more modern versions are digital, and they tend to digitize the spectrum in the same way an SDR does, and they retune in jumps. And so again, you've got that same retuning method. But you're doing it in stages. You're doing it in steps instead, and this allows kind of cheaper and what phrase am I looking for? It enables you to have kind of some more interesting features of your spectrum analyzer and lower cost.
Sure. And one of the things we think of as software-defined radio users and developers is that looking at something like this, that's something we can do with the software-defined radio platform. We can monitor a little chunk of spectrum, and then we can tune it to a new frequency and monitor another little chunk of spectrum, and so forth. And we can, in theory, do the exact same thing as one of these expensive benchtop spectrum analyzers, with some limitations, like we might not be able to do it as quickly, but it's basically something we can do, and it's been done by many folks, notably probably the most popular tool in the open source SDR community for spectrum monitoring in this way is called RTL Power, and it's a pretty lightweight command line tool that works with the RTL SDR, the TV tuner dongles, and those are very low-cost devices that are super useful for their SDR receivers. And this RTL Power program basically just successively tunes that dongle to a variety of frequencies over a wide range and outputs frequency, power versus frequency data. That data is output in a CSV file, so you can just redirect it to a file and save that, or pull it into a database or whatever you want. And there's a fairly popular tool called heatmap.py that it will take that CSV file and turn it into a visualization such as this. It's a spectrogram similar to a waterfall plot, except in this case it's a waterfall that doesn't move. It's a large image that has frequency on one axis, time on another axis, and power represented by the color or the brightness of each individual pixel. And this one happens to be annotated. You can't really see it down at the bottom of the screen because the text is so small, and that's just a side effect of us scaling down an image that is actually very, very large. And somebody has taken the time, Holland, I believe, is the person who had posted this image online. He had taken the time to annotate this and describe what different sections of the spectrum were being used for, different features that were identified in this heat map or in this spectrogram. This was captured over a period of 24 hours. And so even though it is a fairly large image, has a reasonable amount of data represented, the speed at which the speed at which RTL Power operates is rather slow. It requires, over a wide band capture like this is about 2 gigahertz of spectrum. Over 2 gigahertz of spectrum, it requires many seconds just to perform one sweep. And so each horizontal row of pixels was captured over many seconds. And so many transient events were likely to be missed. And we were thinking about this and how we might be able to do better. We specifically wanted to increase sweep speed with HackRF because we thought that we would have some ways we could do that. And we identified sort of 3 different things that could be optimized to increase that sweep speed. One of those is the instantaneous bandwidth, which is how much bandwidth we capture at a time. And that's just simply a function of the sample rate. So just using a platform that has a higher sample rate gives us a wider bandwidth there. And so that's a big win. in our case, we were capturing with HackRF 20 megahertz of bandwidth at a time versus about a tenth of that at a time with the RTL SDR. But we're limited by the maximum sample rate of the SDR platform. Now the capture time can be optimized in theory, however there's a little trade-off there. The less time you spend capturing on any one frequency, the less frequency resolution is available within that chunk of spectrum, within that little brick. And so you can only reduce the capture time so much and still be useful. But the tuning time was very interesting for us to optimize, because the tuning time is just wasted time. This is the time it takes to tune the SDR platform's radio section, its analog section, from one frequency to another. And the more time that takes, the less time overall that you're actually collecting the information. So if we can optimize the tuning time, if we can really reduce that tuning time, then it's a big win in terms of making all this capture less sparse and giving us more information over the same period of time. So we were looking at that, and in the fairly early days of HackRF, we kind of recognized that we would have an opportunity to optimize our tuning time in one very important way, and that is by completely eliminating USB latency. Now, both RTL SDR and HackRF are USB devices that are typically connected to a laptop or some other host computer. And with RTL SDR, the laptop is telling the RTL SDR to tune to a new frequency. And then it captures some information. And then the laptop has to issue another USB command to tell the RTL SDR to tune to another frequency. And those USB commands take a considerable amount of time. There's a lot of latency in USB. So what we've done with HackRF is we've implemented a tool called HackRF Sweep, which is a command line tool that is vaguely similar to RTL Power. But what we do is we also have a little piece of HackRF Sweep that lives in the firmware running on the ARM microcontroller of HackRF1. And the firmware is what controls the sweeping. It's what retunes the radio. So we give one command over USB at the beginning of this operation, and then the firmware takes over and handles all the retuning and just spits data back over the USB cable. And so we only have data going in one direction on the USB cable. We don't have any round trip commands or communication going over that USB link. This greatly increases our sweep rate by considerably reducing our tuning time. Right now we're operating with a tuning time of about 800 microseconds, and when we were doing things over USB, that was a few milliseconds. So we really significantly reduced our tuning time that way.
We've reduced that by at least an order of magnitude.
Yeah.
If not more.
So this is actually a heat map that was produced with output from HackRF Sweep, and we didn't bother capturing for 24 hours like that last picture. How long was this?
We captured this for 2.5 minutes.
2.5 minutes.
And the width of this, the width of the previous image was 2 gigahertz at the side, which is the tuning range of an RTL SDR dongle. The width of this is 6 gigahertz, because that is the tuning range of HackRF. And one of the things that's notable here actually is Mike had to modify heatmap.py to accept timestamps that were in sub-second granularity, because we're able to sweep 0 to 6 gigahertz in 0.75 seconds. So we were getting output from our tool that was having multiple readings for the same frequency within the same second. And heatmap.py didn't like that.
Right.
It was used to taking multiple seconds to sweep that range. So we're able to capture multiple lines of data in the time that RTL Power is able to capture one row of pixels, one single sweep. We can capture a couple of rows, and we're doing 3 times the bandwidth.
And heat map, by the way, if you find the Git repo for that. I don't think my pull request has been accepted, so you might need to grab that pull request if you want to use this.
If everyone would comment on the pull request until it gets merged, that would help us out.
So let's do some demos here before we move on. First thing I want to show you actually is just a little waterfall plot with Phosphor, just so people have a little kind of a visual image of this. I'm going to tune to the 2.4 gigahertz band, which is where we have Wi-Fi and Bluetooth and all that kind of stuff going on. It's a little busy here at Black Hat. I'll set the sample rate to 20 megahertz, 20 million samples per second, which is our maximum, so that increases the bandwidth that we're seeing here. So primarily what we're seeing is kind of on the left-hand side of the screen, there's the upper edge of one Wi-Fi channel, and on the right-hand side we're seeing the lower edge of another Wi-Fi channel. And from time to time, you may see some Bluetooth devices. So as Dominic was mentioning earlier, Phosphor does a great job of kind of solving the problem of missing transient events, and it does that by being very fast and displaying everything that's going on the screen. Now, you may think it's so fast that it may have some limited utility, because hardly any time is actually displayed in this spectrogram before it's gone, right? But it kind of makes up for that a little bit by having this sort of probabilistic display up here near the top. You can see, especially look at this red trace. You can see that there are sort of these 1 megahertz wide mounds that appear. Oh, there are some more. Those are actually individual Bluetooth channels. And so even though a particular Bluetooth packet is barely visible in the waterfall plot and just it strolls off the screen like that, the trend of that Bluetooth channel being used gets visualized up at the top section. It's a pretty nice solution, and it's a solution based on the way that displays of real-time spectrum analyzers work. A real-time spectrum analyzer is kind of the newer type of spectrum analyzer that you can buy. They are quite expensive, tens of thousands of dollars at least, and they are essentially very high-end software-defined radio platforms with a nice user interface. What TNT did was say, hey, we have these lower-end software-defined radio platforms, but we could use them in the same way and get the same kind of data display, and that's what we're seeing here. This is open source software, and one of the reasons it's so fast on a lot of platforms is because it does have the ability to take advantage of GPU optimization. It uses OpenCL, so it's a pretty cool thing. But the biggest limitation here, I think, is that its view is limited to the bandwidth that can be represented with my sample rate. My maximum sample rate is 20 million samples per second here, and that means I can't view more than 20 megahertz wide, which is like the width of one Wi-Fi channel, and that's all I can see at once. But now I'll show you what we do with HackRF Sweep. I'll just run HackRF Sweep here without any arguments, and don't worry too much if you can't see the text on the screen, because what I really want you to see is just how fast it moves. Right now, we're monitoring, by default, HackRF Sweep monitors 6 gigahertz of bandwidth, and every time you kind of see the screen kind of glitch to the side, that's a new sweep happening. So every time that happens, that's a new sweep through 6 gigahertz of bandwidth. I'm going to run that through, oops, didn't need to fill that window, but Q Spectrum Analyzer. Q Spectrum Analyzer is a GUI tool that's designed to be spectrum analyzer, like a benchtop spectrum analyzer, but for software-defined radio. And originally it was written for RTL power, so it supports RTL power as a back end, but we added support for HackRF Sweep as a back end, and this has been, this HackRF Sweep support has been merged by the author of Q Spectrum Analyzer, so you don't have to grab my pull request or anything. And if you select the HackRF Sweep backend, then you can do things like sweep across 6 gigahertz of bandwidth. Now, this is the exact same thing. It's running that HackRF Sweep that I was just showing you in the background, but this time it's visualizing it and it's producing a waterfall plot here. Obviously, this is a much slower waterfall plot than we had with phosphor. The reason it's slower is because we only get one sweep every 3/4 of a second. That's a sweep rate of 8 gigahertz per second. And it doesn't actually matter how wide a bandwidth we choose. We're always going to get, at least with our current firmware and software, we're always going to get a sweep rate of 8 gigahertz per second. So we'll actually get a much faster waterfall if we select a narrower bandwidth.
Right. So right now we're showing 300 times the bandwidth that GR Phosphor was showing minutes ago, and so we're running at 300th of the rate. Whereas if we narrow it down to a narrower band, that was a cube.
Yeah.
Do that.
Then
it will go faster.
But, well, actually, before I narrow it down, I just want to show a couple things.
Okay.
Point out a couple. So here where my crosshairs are centered, that's the 2.4 gigahertz band. So that's that busy band full of Wi-Fi and Bluetooth. But there are some other things going on. One such thing is down here. But generally speaking, the most prominent things you're likely to see are, in an environment like this at least, are going to be the 2.4 gigahertz band and various cellular bands. So this very powerful stuff up here is probably like Dominic's phone. Oh no, mine. I took mine out of airplane mode.
Yeah, there'll also be our microphones. You were looking at those this week, and they are on.
Yeah, those are around here, like this peak right here in the upper 500 megahertz.
And then obviously there's a small peak at 5 gigahertz, which is the other Wi-Fi channels.
Right.
Up there.
And up here at 5.8 gigahertz in particular is some Wi-Fi activity. These microphones, by the way, are pretty cool. They support AES 256, but even though they support AES 256, we found out in my SDR class yesterday that they are vulnerable to replay attacks. So I'm going to stop this and just focus in on the 2.4 gigahertz band, which we were looking at earlier. Now, since I'm only sweeping across 100 megahertz of bandwidth, which is still considerably more than I could get with phosphor, since we are sweeping across only 100 megahertz of bandwidth, we'll get a much faster number of a much higher number of sweeps per second. We're still sweeping at a rate of 8 gigahertz per second. Now that doesn't look too useful, but there we go. Okay, so this is a 100 megahertz wide waterfall plot being produced by HackerF Sweep and visualized with Sweep Spectrum Analyzer.
So this is the entire 2.4 gigahertz Wi-Fi and Bluetooth band and other ISM things, but mostly around here it'll be Wi-Fi and Bluetooth and everyone's phone. And you can see those Wi-Fi channels are big, they're wide, they're very powerful. There's whipping, not one up at the top end. But there are 3 main channels, and they're occupying most of the spectrum. And so we could use this to go and debug, like what's camping on which channel, where are we having interferes, where should we put our Wi-Fi. In fact, we did that in the office. We used this tool to identify that we had an interfering device in our office that allowed us to move our Wi-Fi channel and get a better performance.
Yes. And it's actually not weird that we don't see Wi-Fi up here, because the 2.4 gigahertz ISM band of the United States ends at 2.483, which is right where my mouse is. So this stuff up here is above the ISM band. There are Wi-Fi channels that are not legal in the U.S. but are legal in other countries that are up in this section. And there have been situations where in the United States people have used those not allowed Wi-Fi channels to create, as a very easy way to create covert channels. So this kind of visualization is a good technique to use to find out if somebody's doing that, if somebody's using Wi-Fi on one of the non-standard or non-permitted channels in a given country. Is it time to go back to slides? Is that
What the fuck?
Yeah.
Those are like fucking real life threats.
The
Like,
thing
really,
with
man?
this-
It is.
Like that kind of thing, you can definitely go to police.
Here we go. So this is something we captured in our lab.
It's a little less busy there.
Yeah, you can see that we have a one Wi-Fi network and maybe some stuff leaking through from the neighbors. You can also see this area here with our interfering device, which was our microwave oven, and it leaks far more than we anticipated. And we were taking this work like 20 meters across the lab.
Yeah.
So like
And at least.
yeah, it leaks a lot of 2.4 gigahertz RF in comparison to our Wi-Fi router, which was in about the same spot, which gives out this, and the brighter the color, the more power there is there. Now, one of the things you might notice if you look at the Wi-Fi packets that we've received is they've got these weird chunks missing out of them. And this is another artifact of an optimization in the technique we use to produce this high sweep rate. When we were receiving using Phosphor, you may have noticed that there's a spike in the middle of the display. And if you've used SDR technology that does complex sampling before, you have seen this, you'll know what it is. It's the DC offset. It's just an artifact of the way we sample, and we didn't want that clouding the display. It's perfectly valid data, but it causes problems in waterfall plots and FFTs because we'd end up with a lot of very straight lines, high power lines across this thing, and especially if we're doing a 6 gigahertz wide sweep, we're doing 300 captures, we would end up with 300 vertical lines that would look like they were more powerful than our thing. So we don't want that, so we came up with a technique to cut that out, but we still want to see those frequencies. We can't just throw away information about certain parts of the spectrum because we don't like it. So what we do is we capture on a frequency for a period of time, calculate those at the FFTs to produce the power measurements. We then shift by 5 megahertz, capture again, create another set of power measurements, perform FFTs to get those power values, and we then chop up that data and recombine it so that we always remove, there it is. So we always remove the center section of any capture and the two edges. We remove the two edges because we have a bandpass filter that tries to filter out other data, and that rolls off of the two edges. So while we can get 20 megahertz of bandwidth, the middle 15 are kind of the most representative, and if we're doing this shifting method, the maths worked out nicely. That what we do is for 20 megahertz of received data, we get two 5 megahertz chunks. We shift by 5 megahertz, get two more 5 megahertz chunks, and then put them all together to generate a 20 megahertz chunk. So what you're seeing in this slide with these Wi-Fi packets that we received is you're seeing the Wi-Fi packet had stopped being transmitted at the point that we shifted and received the surrounding pair of 5 megahertz signals. 5 megahertz chunks of spectrum, and so you get these slightly weird artifacts sometimes in there. But given that we're sweeping this data so quick, we're never trying to actually pull data out. We're never trying to demodulate these signals. We're not trying to receive these packets because we're sweeping past them too quickly. Our duty cycle is low enough that we wouldn't get any useful data from that. The idea is we're trying to get an overall big picture view of the spectrum, and then we can drill down into those, at which point we won't lose those chunks anymore. So we think this is a pretty valid thing to do, and it gets us, it slows our sweep rate down, but it gets us much higher quality data. Now, Mike likes to spend time teaching people about the FFT, and sadly we don't have time for that, but he will happily do that in the wrap-up room for an hour or two. But one of the things he likes to tell people is it's completely reversible. It's a transform. It doesn't throw away data. It converts data from the time domain, so that's samples over time, to the frequency domain, that's power versus frequency. And we can run that backwards. And so the only reason you want to run that backwards is to recover the original data a lot of the time. But one of the things we like to do, because we're already chopping up our FFTs and our spectrum, is we like to chop them up and rearrange them into one huge chunk, and then run that backwards, through the inverse FFT algorithm, and produce time domain signals as if we really received them. So what we're doing is as we step through, we're taking a small chunk of the time domain, and then we're reassembling them in the frequency domain to be consecutive, at which point we invert the FFT, and we get back time domain samples as if we had a 6 gigahertz radio. So we take a 20 megahertz bandwidth radio, and we produce data that's artificially at 6 gigahertz wide. Now, we're not producing 6 gigahertz of data at that full rate. We're producing it in chunks over time as we sweep. But
Right.
we're able to, the reason we like to do this is there are a lot of interesting tools out there that help us analyze data captured from radios in time domain signals. And so when we produce these time domain signals again, we can go and use all this existing software and all these existing tools and techniques that we already know about to analyze this data. And one of those is, as we've already demonstrated, phosphor. And
Yeah.
so that should work with.
It should work. I just want to mention that. So what we're producing here is, if we are sweeping across 6 gigahertz of bandwidth, regardless of what our sample rate is, which is usually 20 megasamples per second, but regardless of what our sample rate is, after a sweep and after this inverse FFT, we come up with a short burst of simulated samples at a rate of 6 gigasamples per second. So even though we don't have a 6 gigasample per second ADC, we can simulate that with you, and as Dominic mentioned, for a very short period of time, and then we get another burst a little bit later, once per sweep. And as Dominic mentioned, that lets us kind of take advantage of some tools that already exist without having to modify those tools. Now, I failed to completely set up my demo, but I'll just do it right now. I have to do a funny little name type thing. This inverse FFT trick, most of the stuff we're talking about is already released in the previous release of HackRF that happened a few months ago. But the inverse FFT trick is something new that you have to get code out of Git to work.
Would you like me to talk about it while you talk? Yes, please, that'd be easier. Okay. So the inverse FFT trick involves, it was built into the HackRF sweep tool, but because we want to get it into other tools, and it's not supported by GNU Radio or anything like that just yet, and we'd like to work on that with other manufacturers to have everyone be able to do interesting sweeping things simultaneously. But right now we have to push it through a named pipe in our system and read it from GNU Radio as if it's a file, and this works pretty well. I don't know.
Really close.
Excellent. That looks like a very complicated flow graph.
Yeah, I'll make a simpler one. Let's do, let's actually have a whole GUI on screen here. What I'm doing here is I'm just reading in a file that is actually a named pipe, and then I'll just dump the output into phosphor.
It's really a two-block flow graph. It's
Yeah.
simple. We just name pipe in there, and it should.
And I'm going to tell phosphor that I have a sample rate of 6 gigasamples per second.
Alright.
Sure, you can call it untitled. Why not? Now it's waiting for some data. As soon as I start feeding it data from HackRF Sweep, I can actually make this go faster if I were to give it a smaller FFT bin width.
So the amount of data we get out of the inverse FFT is equal to the amount of data we
Put
put into it. And so if changing our FFT bin width changes the amount of data we use versus the amount of data we throw away. And so by reducing the bin width, we calculate a higher granularity of sample of FFTs. And that gives us a higher data rate than we come back out of the inverse FFT. So what you can see here is this is 6 gigahertz wide sweep again, and it looks like that data that we saw from Q-Spectrum Analyzer previously, with the same peaks, the same spikes. So we know it's good data, but we can view it in GR Phosphor, and we can view it in other tools such as in Spectrum, and we can take it offline and analyze it there.
Yeah, and the principal benefit here, obviously we're seeing overall a display kind of similar to what we saw in Q-Spectrum Analyzer. But the principal benefit of this inverse FFT trick is that it gives us the ability to pipe our data into an off-the-shelf SDR visualization tool like Phosphor without having to even modify Phosphor. let's try this again, just looking at the 2.4 gigahertz band, because it just looks cool. And I'm just fooling Phosphor into thinking it has a 100 megahertz sample rate, even though it doesn't really, well, I mean, it does, but only in short bursts. And this can even be made to go faster. Let's see if we can, let's see if we can push it a bit. Neat, huh?
So again, we're seeing the 2.4 gigahertz band. We're seeing those three big Wi-Fi channels and that drop off at the end. But we're seeing a much higher data rate than we were in Q-Spectrum Analyzer. We're getting better granularity. We're much more likely to see transient events here, and we're able to use this tool because of the intercept feature. Let's get back to the slides because we have more to cover.
Oh, but I want to just see how far we can go.
Now is not the time. All right, so we can get much faster.
It might be a little jumpy because my CPU might not entirely be keeping up with this.
So at some point, the limitation there is the number of samples we receive on the HackerF, and that there is a trade-off from that earlier diagram of capture time versus amount of data we can get out. But the real limitation there is the CPU power that Mike has on his laptop. So we will actually be at Black Hat Arsenal tomorrow afternoon. I can't remember what time. But we'll be, if you look at the schedule, you'll find us there. We'll be talking about all these various different tools and techniques and trying to combine them together. And one place we've been trying to do that is a tool called Shiny SDR. It's a web-based platform developed by Kevin Reed. Its backend's written in Python and uses GNU Radio, so it's super easy to extend and modify. You get waterfall plots, you get demodulators. So this is what it looks like. This is a web interface. You put this on a box, like running on a little server somewhere in your environment, and you can remotely monitor that environment, which we think is a really interesting technique. You can see here that we were using that HackerF sweep technique again because this. There it is. This chunk here is a Wi-Fi channel, and it just suddenly cuts off in the display. These slides will be online for anyone who's taking pictures of them. We'll put them up this afternoon. This also gives us the opportunity to have multiple radio sources simultaneously. It allows us to have receivers, and those receivers can do interesting things with the data. They can analyze it in ways that we've been experimenting with, and we'll come on to in a minute. And it also enables us to tag. It's simple for us because we like to know what the data is going on, what those signals represent. And so here you can see gigahertz band and is an amateur band and various other things, and it's tagged in the display. So you've got a real-time idea of, like, do I care about what this signal is, and what is this signal something I know about to represent my environment? So one of the things we might want to use the demodulators and the decoders for is modulation classification. Do you want to talk about it?
Sure. Yeah, so this is something that I've been working on lately, and happy to talk to people about tomorrow in our Arsenal demo and later at our wrap room this afternoon. But there's some existing open source software already, specifically in a tool that's based on GNU Radio called GR Inspector for automatic modulation classification. And we think this is really important in the long run to try to integrate with some of these other spectrum monitoring tools, because somebody who is an expert in SDR can look at a waterfall plot and very often identify modulation and say, that looks like on-off keying, that looks like QFSK, that looks like QPSK, and so forth. That really, we should have tools that can help us do that even for non-experts. And that's the direction that we want to go. So I've been looking at the implementation in GR Inspector, which is based on TensorFlow, and trying to see if I can get that integrated into Shiny SDR or some other tools. And one of the things I'm starting to look at is maybe there's something kind of simpler than a neural net that could be used as a first pass to identify some of the simpler modulations. But the more complex modulations are probably things that the neural network approach makes sense for. This is a little screenshot from GR Inspector that doesn't actually show the automated modulation classification feature being used, but it does show how automated power detection is working to identify bands. And so then these bands can then be automatically, once they've been automatically identified, they can be fed into a classifier.
So going back to this slide from earlier, the drawbacks from the waterfall, in mistransient events, we have limited amount of time span and limited bandwidth, and we can, I wouldn't say solve those problems, but we can work around those problems using techniques like HackerF Suite, using GR, Phosphor, using Q-Spectrum Analyzer, and get more information, and heat map also helps us there solve those problems. So one more thing, which we actually didn't run our demos using this today because it was pretty new, but one of the issues that you may know if you've played around with radio SDR a lot or worked with SDR and radio in general is you need to pick a good antenna, because we're looking at the amount of power on the radio spectrum at a given point in time, where we need to know that power level that we're looking at means something. And if our antenna is not tuned to the frequency that we care about, that we're looking at, then we're going to see lower power levels than we would anticipate, and we're going to see artifacts and things like that. So we want to have a better idea of how we want to have a better view of the spectrum. And one of the ways we do this with an antenna switching board, which is attached to the top of our HackerF here, and as you can see in the diagram, and in the image. And this is a test we were running in the hotel room last night, that we have multiple antennas hooked up to the switching board, and the HackerF knows which antenna is attached to which. We tell it in advance which antenna is attached to which port. And then the HackerF has firmware which knows to switch antenna ports to the appropriate antenna for what it's trying to receive at the time that it retunes. And this runs very quickly, and so we're able to run it at a fast enough rate that we can keep up switching antennas in with HackerF Suite at about 0.75 seconds for a complete sweep. It can switch back and forth between those antennas more than quickly.
Yeah, since it's implemented in firmware, the antenna switching happens in a matter of several nanoseconds, which is way less than the time it takes for the thing to actually tune to a new frequency. So we can arbitrarily choose a new antenna every single time we retune the radio with no trouble at all.
So another thing this board can be used for is to do direction finding. If we want to have a better idea of what's going on around us wirelessly, we might want to actually find a physical device. We might want to know where that device is coming, signal is coming from. And the gentleman on screen is Mike Davis, and he's going to be giving a talk tonight at the Cyber Spectrum event at the SynShop Hackerspace. And he's going to be talking about direction finding using this technique with our antenna switching board. And he will use pseudo Doppler to switch between these very quickly to look at phase shift that gives us that information about direction finding. So that's worthwhile if you have no other plans tonight.
Of course, it's up against the Pony Award, sadly, but
yeah.
Both Ponies and the Cyber Spectrum are good things for you to do tonight. Cyber Spectrum is great with not just Mike Davis speaking, but a whole bunch of SDR enthusiasts getting together and talking about projects.
We are out of time, but we'd like to thank the people on the screen, Kevin Reed for Shiny SDR, and Mike Walters for his help with HackerF Suite, Miguel Krenek for Q-Spectrum Analyzer, and we had a couple of interns this summer who added some features to Shiny SDR for us. So Jacob Graves and Ellie Pulse, we'd like to thank them both. And we will take questions in the wrap-up room now.
South Seas H.
South Seas H, if you have any questions.
H. Thanks, everybody. Yay, all right. Hey, thanks everybody for coming. This is super exciting to be here. It's been a few years since I've had a talk here at DEF CON, and it's great to be back. I'm Michael Osman of Great Scott Gadgets, and I make hardware for hackers. So, I spend my time completely devoted to building open source hardware primarily for the information security community and for other innovative people. So this is the NSA playset RF retro reflectors. Hopefully some of you have noticed this isn't the only NSA playset talk on the schedule. Some of my cohorts are in the front row here, and we have talks coming up soon. The concept of the NSA playset is, now that the ANT catalog has leaked, and it leaked last winter, we in the open security community suddenly have a glimpse of what the NSA uses, at least in some cases, for their hardware and software as attack tools and the implants. Hopefully some of you have seen. The concept of the NSA playset is that now that we know those things, let's build them ourselves. Let's create similar capabilities using open source hardware and open source software, or off-the-shelf hardware, anything that's readily available, very accessible. Try to make this stuff easy to use and try to raise awareness about the security implications that of these technologies existing at all. I gave a talk with Dean Pierce, who's in the front row here, at Tour Camp, and URL's up there. You might be able to read it.
Well, don't you like it then?
Color's a little off, but most of my slides are black and white anyway, so who cares? If you're interested in a little bit of a background in the NSA playset and a broad overview of what's in the ANT catalog and how we think these things can be made in the open community, that's the best place to start. That's the introduction talk to the series. And this weekend here at DEF CON, a number of us are doing talks on the specific parts of the NSA playset. Today I'm talking about RF retro reflectors. Oh, and last night, by the way, how many of you were at the EFF summit last night? Yeah? Really? That's it?
Oh, Mr. Blackadder, leave me alone, boy. If I wanted to talk to a vegetable,
at the summit, I know a lot of you were there. And a bunch of us from the NSA playset cabal got together and donated a whole bunch of hardware. So we made this cool playset bucket. It's got ROPS in it, and it has IMEs, and it has PCI Express attack tools, Thunderbolt attack tools, it has an hard drive full of rainbow cables for GSM, I mean, just on and on and on. Huge kit, and it went for $2,250 in the auction last night. So thanks to everyone who contributed and who bid on it. Is the winner of the auction here?
I want books written about me. I want songs sung about me.
Well, I'd like to shake your hand at some point. That was pretty amazing that we were able to put together and do that. So my talk today is on the RF retro reflectors, similar to those that are in the ANT catalog. And an RF retro reflector is... well, and I've never heard the term RF retro reflector really before the ANT catalog leaked, so I've kind of adopted it, but it's a little implant that
and you live in the
modulates an incoming radio signal and reflects it back to the radar device that's illuminating it. So the attacker's on the left, and the attacker fires a radio wave at the target. The target has a little implant that reflects that radio wave back to the radar unit being used by the attacker. The process of irradiating a target is often called illumination. You kind of think of it as shining a light on the target. The light happens to be radio wavelengths instead of visible wavelengths, but otherwise it's the same thing. You're shining a radar beam at a target, illuminating it, and seeing what gets reflected back. And then the implant is some very small device that is designed to modulate the reflection. And this can be done at extremely low power, which is one of the reasons that this approach is useful. It can be done with no battery, for example. It can be completely powered just by the radio wave itself. So it's a super simple kind of implant design. that is very low power and uses a very small number of components. So it can be tiny and it can be without any local battery source.
He's
So that's
better
the
than
kind of
Mad
thing I'm
Jack
talking about
McMahon,
today.
the winner of last year's Mr.
And I kind of want to set the record straight a little bit. One of my earlier talks got some press,
The
and
walrus awakes.
people were writing that I was reverse engineering tools in NSA AMP catalog, and I don't think that's actually correct.
Moving about.
I don't have any devices from the NSA. I don't have any inside knowledge of devices used by the NSA. All I have is the information that's in a public leaked AMP catalog that anyone can find leaked on the internet. So I'm not really, I don't really feel that I'm reverse engineering the NSA's tools. I'm forward engineering tools that have similar capabilities to those that the NSA uses. And hopefully this will help us in the open community create a set of tools that we can use to research this kind of capability and find out how it works and how well it works, what the implications are, and whether or not these things can be made much in the future, much more sophisticated than we know of now.
Flying through the London nights, bound
So in
for
this
the
talk,
ladies'
I will
Which
cover
lady's home is
leaked
this?
classified
home for the
information from the
elderly or
AMP
a home for
catalog.
the
I don't think
mentally
I put any
disadvantaged?
screenshots in here from the AMP catalog, but I'm going to talk about things that I've observed
Yes,
from the
sir.
AMP
It is the seat
catalog.
of the
So
Duke of Wellington.
if you don't
Those ladies, I
want
fancy,
to
would be
hear
with
about leaked classified information, you can leave now. Anyone
Oh,
bringing
I
this back
spent
to
a
bed?
night of ecstasy with a pair of Wellingtons and I loved it.
I am going to show you in this talk a few hardware designs for my own retroreflectors, and I'm going to tell you how to build your own retroreflector right here at DEF CON if you want.
Fighting the French.
I'm also going to do a live demonstration,
triumphed 6
and
months ago.
really kind of the reason I'm doing all of this is to lure you here so that you can listen to me rant about the state of emission security.
Not really, no.
Emission security is the field
But I fear
of
France
security
will
where
not
we
follow.
study emissions
Well, how's your
from
Mongolian?
devices, and a fair bit is
But I
known
fear
in the
Wellington is a
public
close personal friend of
research
the Chief
community, the
Mongol.
hacker community,
They were deep
about passive attacks.
Doomed as a dodo.
But not very
Oh my
much
God, he's
has
here,
been
Wellington's
known
here already.
historically about
Oh, you're
active
going to
attacks.
forgive me.
And
Forgive me. I
today
don't know
I'm
what
talking
doing. I'm a
specifically
bad,
about
bad,
active
sexually overactive
attacks, where
fool.
an attacker actually
You're perfectly safe.
transmits something
Hurrah!
towards
Until
the
6
target.
o'clock tonight.
The
Peru.
From
passive
Supreme
attacks
Commander,
that we
Allied
know
Forces
about,
Europe, sir. Prince or pauper, when a
you may
man
have heard the
soils a
code name
Wellington, he
Tempest.
puts his foot in it.
and sometimes people apply the word Tempest to
Not
kind
a
of
joke.
all of emission
I do not
security,
find my name
but
remotely
really it's a
funny,
code
and
name that
people who
relates
do end up
specifically
dead.
to unintentional
I challenge you
emissions.
to a duel
Now there are all
tonight at
kinds of different
1800 hours,
unintentional
in which you
emissions.
will
There are
die. Yours with
RF
sincere apologies
emissions,
for your
there are
impending violent
conducted
slaughter. The
electrical
world is
emissions,
good Wellington.
thermal
Sounds nice,
emissions, audio, all kinds of things. There are all these different little side channels where
Don't worry,
somebody
sir, please.
might
Just
be able
consider that
to
life is a
pick up
valley of
some kind of
woe
an
filled with
unintentional
pain, misery,
emission
hunger, and despair.
and
Well, not
from
for me,
that
it isn't.
information
As far as I'm concerned, life
figure
is a
out
big
something
palace
about the
full of
state
food,
of the
drink, and
target.
comfy sofas.
And in some cases, figure out extreme information about the state of the
The
target,
prince is
like
about to die. The last thing
reproducing
he
what's
wants to
on
do
the
in his
video
final
screen
moments
or
is exchange
capturing
pleasantries
strokes,
with a
so forth.
certified plum duff.
So there's a fair amount of research
Let's hear him out.
in the area of passive emission
then
security
throw
attacks. If you want to get started reading about these things, probably the best place to start would be the writings of Marcus
Don't
Kuhn.
listen to him, sir. Cruel
the-
proletarian trick to raise your hopes.
I do
shall
think
have
there
you
is
the
quite a
moment
bit
he's
of
finished clearing away your
opportunity in the field of passive emission
This
security for
disgusting,
future
degrading
research.
creature is
There are lots of
blessing in
things that are
disguise.
unexplored at this time. However, we at least have a little bit of information and a little bit of public research, and you can find here. That's not quite true so much for active attacks.
Well, Your Majesty,
Active
I
attacks,
just thought this Wellington
the
bloke's
main
been
thing
here
that we've
for
known
years.
about for
You
years
don't know
that
what he
everybody
looks like, you
always
don't know what
talks
you
about
looks like.
being
So why don't you
the
get
prime
someone else
example
to
of
fight the
active
duel
emission
instead of
security is the
And
thing.
Prince
The
Regent's
Great Seal bug.
portrait hangs on every
This
wall.
was a bug that was discovered
My cousin Bertie,
inside a wooden
Mr.
carving of the Great Seal of the United States
he says
in
that
the
he's
U.S.
heard
Embassy
that
in
all portraits
Moscow.
are the same these days,
And
because they're painted
information
to a romantic
about this
ideal rather than
bug
a
was
depiction
released
of the
publicly in
idiosyncratic facial
1960.
qualities of the person in
It
question.
was supposedly discovered in the early
Your cousin
50s
Bert obviously has a
and
larger
may have been
vocabulary than you
implanted as early as 1945.
Damn him.
So this
Anybody
is
could fight the Duke.
from
All
this is
Willers would never
technology
know.
from
All
the
the same, sir, Baldwin's
mid
plan does
to
seem to
early
hit
40s.
on finding someone willing to commit
And
suicide.
it's an
on your
incredibly
behalf.
simple device.
Yes,
It
yes, but he would be
consists
fabulously
of
rewarded.
a
Money,
microphone
titles,
and
castle.
an antenna.
That's
And
right.
that's it.
I thought
It
maybe
doesn't
Mr.
have
Blackadder
any
himself
active
fancied the
components
job.
whatsoever.
What a
It
splendid
simply
idea.
is a
Excuse me,
condenser
Your
mic,
Highness,
which is
trouble with the stuff.
a capacitor that changes its capacitance based on the air pressure. And that is connected to an antenna in such a way that the air pressure changes in the air
and
pressure,
telling
which
the
of course
prince that you walked over a
changes
very
in air
sharp
pressure our
cattle
sound.
grid in an extremely heavy
The changes in air pressure modulate the
You was
impedance
only just
connected to
saying
the
in the
antenna,
kitchen how you
and
wanted
that
to rise
modulates
again.
the
Now here the prince
reflection
is offering you the
that
lot.
comes
But
back to a
tiny,
radar
tiny
unit
brain, the
that is
iron juke will
illuminating
kill
this
me.
device.
To even think about
In
taking
some
him on, you have to
ways,
be
it
some kind
is
of homicidal
very
maniac who's
difficult to
fantastically good
detect
fighting
because
like Makada.
it's not active most of the time.
Makada
You
can fight
wouldn't,
that
if
duel
you
for me.
looked around to try to see,
I was just
like before a big
having a
meeting,
word with
you
my
went around
insurance.
looking for you would pick up nothing from this thing. But
God,
it, once the meeting starts and your attacker starts illuminating this device with radar, then suddenly it is active.
Suicide
And
policy. There is
it
an unusual clause which
uses
states
no
that the
power,
policy
no
holder
local power
must wear a
supply
big red wig
whatsoever.
and
And
affect
it's a
the Scottish
pretty,
accent in the combat zone.
it's a pretty incredible invention for the time. The next thing, I mean, I
Now I
think
gather from your look of tired
everybody's heard
exhaustion
about
and the
now
globules of
that we've had
courage
these
hanging
RF
off the wall,
retroreflectors in
that
the
my
ANT
cousin
catalog.
Makada
So what
has
happens
presented
in
his
between
credentials.
the thing and the ANT catalog? We had 53
I hope
years
you've
of
been
rumor and
practicing
speculation.
this Claymore.
I should
And
say so.
I wish I
And
were
as
exaggerating,
weary as a dog with no legs
but
that's just climbed Ben
really,
Nevis.
if you look for hard evidence, if you look for
See this intricate
example
carving of the
designs,
infant
if you look
Samuel
for
at
somebody who's done an
He
actual
whittled that with the
experiment
tip
to
of his
show
mighty
how
weapon with
an
his eyes
active
closed.
emission security attack works,
He bid me. Right
you'll
on the
find
clock.
almost
There was a
nothing
whirlwind of
between
steel, and within a minute,
1960
three men lay
and
dead, and I had
2013.
a lovely new set of napkins.
It is such an unbelievable
Well, look,
gap.
just tell him to
We
meet
are
me here at 5
decades
o'clock, will you, to
behind
discuss an
the
extremely
intelligence
telling plan.
agencies
If
in our
all goes
basic
well, by
understanding
tomorrow,
of threats
the clan
against
of
our own
Makada
system.
will be marching the high road
And-
back to glory.
Now, some people will argue with me. Some people will say otherwise. They'll say, "Oh, I know
This
all
evening I
about
will carve the
these
Duke into
active
an
attacks,"
attractive
and
piece
they'll
of
rattle
furniture
off
with
some
excellent
code words, and they'll mention some declassified documents.
Your Highness.
And you know, I
Oh,
say
thank
to
goodness
them,
you, Blackadder.
POC or
I just had word from
GTFO,
Wellington. He's on his way here now.
because yeah, we've
Must
had a
believe
lot of
from the very
hints.
start that I
We've
am
had a lot of
the one.
hints from
Any ideas?
declassified documents
There's no
over the
alternative.
years.
We must swap
We've
clothes.
had a
Fantastic. Yes,
lot of
dressing up.
speculation that show me the one place where somebody's done a research paper, show me the one place where somebody's given a conference talk, released a hardware design, done an experiment, published the results,
Excellent.
and I personally haven't found it. I'd love if somebody just like came up here and proved me wrong. That would be amazing. But I've been looking, and I haven't found it. Now, the one thing I found, a brief
And you'll have to
mention
get used to
in the
calling
paper
me
Soft
Your
Tempest by Marcus Kuhn and
Your
Ross
Highness.
Anderson.
Your Highness.
They do mention
No, just Your Highness.
an attack
That's what
where
I said. Your Highness. Your
a
Highness.
keyboard
Your
cable,
Highness.
a computer keyboard cable, is irradiated, and
Complicated stuff, obviously.
key presses were detected by the return from that cable. Now, this I would put in the category of rumor and speculation because it's just one
Two
brief
people you know
mention in
well
the
have
paper
exchanged
about
coats, and now you
other
don't know which is
things,
which.
and it
I'm pretty
comes from
confused myself.
a declassified German document. With, you know, as far as I know, no one's ever
Certainly is the man
actually
of the book.
tested this in a public experiment.
On the porpoise?
And one of the interesting things here is that this is apparently
Right, yes, sir.
irradiating,
Let's have to fill in
illuminating
as best we
an
can.
unmodified
Sir, if you
keyboard
would let the Duke
cable.
in.
Certainly. Your
Unmodified.
Highness.
No
Your Highness.
implant was intentionally installed in the target.
And you better get out too.
They,
Yes.
the equipment out of the box vulnerable to this attack, which is quite interesting to me.
The Duke
The-
of Wellington.
And there are some hints in the ant catalog that suggest similar attacks are possible on other things. For example, there's a VGA video implant that is a retro reflector for picking up the video signal. And on the page describing that implant, it says that it provides an enhanced return, which suggests to me that they get some kind of return sometimes from VGA cables without enhancing. That's very interesting. Post-ant catalog. Just this year, there have been some public, on YouTube, some experiments that this one person, GDPR, has posted. So I recommend you check those out. As far as I know, he and I are the only people who've been playing with this stuff and talking about it publicly.
Signed, Wellington.
So today, I'm releasing open source hardware designs for actual implants. And I'm teaching you how you can build them yourself and how simple they are. And